Hey everyone, welcome back. Today we are going to solve a very common interview problem called remove element. At first glance, it looks simple, but this problem is actually a great way to understand in-place array manipulation using the two-pointer technique. If you have ever felt confused about when to move which pointer or why we return a length instead of an array, this video will make it very clear. We will go step by step, visually and calmly, no rushing. By the end of this video, you won't just solve this problem, you will understand a two-pointer rule that you can reuse in many interviews. Let's get started. Before we jump into solving the problem, let's quickly understand where this problem fits. In array problems, the two-pointer technique appears in different forms. Sometimes both pointers move in the same direction, like a slow pointer and a fast pointer. Sometimes pointers start from opposite ends, one from the left and one from the right. And in some problems, we even move pointers backward to avoid overwriting values. The problem we are solving today, remove element, belongs to the same direction two-pointer pattern. Here, one pointer scans every element and the other pointer decides where valid elements should go. Once you understand this category, problems like move zeros and remove duplicates start to feel very similar. So as we solve this problem, don't just focus on the answer. Try to recognize the pattern. This roadmap will help you connect many problems together. Now let's clearly understand the problem. We are given an array of integers called nums and another integer called val. Our task is to remove all occurrences of val from the array. But there is an important constraint here. We must do this in place, meaning we are not allowed to use extra space. Also, we are not asked to return the modified array. Instead, we return the number of elements remaining after removal. So, only the first part of the array matters. Anything beyond the returned length can be ignored. So, as we solve this problem, focus more on how many valid elements remain, not on the exact final arrangement. This detail is very important for interviews. Let's understand this with a simple example. Suppose the array is 3, 2, 2, 3 and the value we want to remove is 3. After removing all occurrences of 3, the remaining elements are 2 and 2. So the new length of the array is 2. We return 2, not the array. The elements after the first two positions does not matter. They can contain any value and we can safely ignore them. So our goal is not to rearrange the whole array perfectly. Our goal is to make sure that the first k elements are valid. Now let's see how we can achieve this efficiently. Now before jumping to the optimal solution, let's look at a very common first thought. One simple idea is to create a new array and copy only the elements that are not equal to val into it. This approach works logically, but there is a problem. We are using extra space and the problem clearly asked us to solve this in place. So even though the solution gives the correct result, it does not satisfy the constraints. That's why we cannot use this approach. Instead, we need a way to remove elements inside the same array without creating a new one. This is exactly where the two-pointer technique helps. Here is the key idea that makes this problem simple. Instead of trying to remove elements from the array, we keep the valid elements and override them inside the same array. To do this, we use two pointers. Pointer j will scan every element in the array, and pointer I will track where the next valid element should go. Because we are scanning the entire array, both pointers start at index 0. At this point, we are not moving anything yet. We are just setting up the roles. Once this setup is clear, the rest becomes mechanical. Now we scan the array one element at a time. At each position, we ask just one simple question. Is the current value equal to val? If the value is equal to val, we simply skip it. If the value is not equal to val, we keep it. At this stage, only pointer j is moving. Pointer I stays where it is. We are just deciding, not modifying anything yet. Once we find a valid value, we will see what to do with it next. Let's walk through this step by step. At the beginning, both pointers I and j are at index 0. The value at index 0 is 3. Since this value is equal to val, we skip it. So in this step, only pointer j moves forward. Now pointer j points to the next element, which is 2. This value is not equal to val, so this is a value we want to keep. We now copy the value at pointer j into the position pointed to by I. This overwrite happens inside the same array. No extra space is used. After copying, we move pointer I one step forward. Pointer j will continue scanning. At this moment, you might see duplicate values in the array. That is completely expected. Only the first I elements matter. We repeat the same exact steps for every element in the array. There is no new logic after this. We continue repeating the same steps. Pointer j keeps moving forward, one element at a time. Whenever we see a value equal to val, we skip it. Whenever we see a valid value, we copy it to position I and move I forward. In our example, pointer j now points to the index 2 with value 2. This is again a valid value, so we copy it to the position I. Then we move I forward. Finally, pointer j reaches the last element, which is 3. Since this equals val, we skip it. Pointer j now reaches the end of the array. At this point, the scan is complete. Pointer I now tells us how many valid elements remain. So the final answer is the value of I. We return I. We do not return the array. Only the first I elements matter. Let's quickly recap the dry run step by step. In step 1, pointer j points to 3. Since this value equals val, we skip it and move j forward. In step 2, pointer j points to 2. This is a valid value, so we copy it to position I and move I forward. In step 3, pointer j again points to 2. We repeat the same logic, copy and move I. In step 4, pointer j points to 3 again. Since this equals val, we skip it. Notice how the same two rules repeat. There is no new logic in any step. So here, final value of I is 2. J always moves and I moves only when value is not equal to val. Let's quickly summarize what just happened. Pointer j scanned the entire array from start to end. Every time we found a value equal to val, we skipped it. Every time we found a valid value, we copied it to the front and moved pointer I. After the full scan, all valid elements are now grouped at the beginning of the array. Pointer I has stopped at position 2. This means there are 2 valid elements in the array. So the final answer is 2. We return the value of I. We do not return the array. Only the first I elements matter. This completes the dry run. Now let's move on to the remaining details. Before we finish, let's quickly talk about edge cases. The good news is we do not need any special logic. If all elements in the array are equal to val, pointer j will skip every element. Pointer I will never move, so the returned length will be 0. If none of the elements are equal to val, every element is valid. Pointer I will move for every element, so we return the full length of the array. If the array has only one element, the same logic still works. We either skip it or keep it and return 0 or 1 accordingly. It also does not matter where val appears, at the beginning, at the end, or in between. The scanning pointer handles all positions. So in every case, the same 2-pointer logic applies. No special conditions are required. Now let's summarize the entire solution in clear steps. First, we initialize 2 pointers, I and j, both starting at index 0. This is because we are scanning the entire array. Next, we traverse the array using pointer j. Pointer j scans every element from left to right. At each position, we check whether the current value is equal to val. If the value equals val, we simply skip it. If the value is valid, we copy it to position I. After copying, we move pointer I forward. Pointer j always moves forward to continue the scan. Once j reaches the end of the array, the scan is complete. We return the value of I as the new length. We do not need to return the array. Before jumping into actual code, let's write this logic as simple pseudocode. This helps us focus on what we are doing without worrying about syntax. We start by initializing 2 pointers I and j both to 0. While pointer j is inside the array, we keep looping. If the value at j equals val, we skip it by moving j forward. Otherwise, we copy the value at j to position I. Then we move both pointers forward. Once the loop finishes, we simply return the value of I. That's the new length of the array. Notice that this pseudocode is the direct translation of the steps we just discussed. There is no new logic here. Now, let's look at the problem on LeetCode. We are given an integer array called nums and an integer value called val. Our task is to remove all occurrences of val from the array. But there are 2 important details here. First, we must do this in place. That means we are not allowed to use any extra array. Second, we are not asked to return the modified array. We only return the number of valid elements after removal. Only the first k elements of the array matter. Anything after that can be ignored. This is a very common source of confusion in interviews. If you look at the constraints, the array size can be large, so we need a solution that works efficiently. Because we are modifying the array in place and scanning it only once, the 2-pointer approach fits perfectly here. So, before we write any code, our focus is not on rearranging the entire array. Our focus is simply to make sure that the first k positions contain valid elements. With that clarity in mind, let's implement the solution step by step. Let's start with the function. I will use two pointers. Pointer I tracks where the next valid element should go. Pointer j scans the array. Both I and j starts at 0 index. We scan the array using j one element at a time. Here is the key check. Is the current value equal to val? If it's not equal to val, this is a value we want to keep. So we copy it to position I. This override happens inside the same array. Then we move pointer I forward. Pointer j always moves forward to continue scanning. If the value is equal to val, we skip it. That means we only move j pointer. We repeat the same steps until j reaches the end of the array. At the end, pointer I tells us how many valid elements remain. So we return I. This is our entire code as we discussed in the pseudocode. Now let's run it. It ran successfully. Let's submit. Alright, that's accepted. Now let's step back and analyze it. If you look at the code, we use a single loop. Pointer j scans the array from the first element to the last. Each element is checked exactly once. There are no nested loops and we never go backwards. That's why the time complexity is O of n. Now let's look at space complexity. We don't create any new array or extra data structure. We only use two pointers, I and j. No matter how large the input is, these take constant space. So the space complexity is O of 1. That's the efficiency of this approach. Simple, optimal and interview friendly. Before we wrap up, let me leave you with one very important rule. This rule will help you decide how to use two pointers in many problems. If your problem involves comparing with previous elements, then pointer j usually starts from index 1. If your problem involves scanning every element, then pointer j starts from index 0. In remove element, we were scanning everything. That's why both pointers started at index 0. Once you recognize this, two pointer problems become much easier. You are no longer guessing, you are following a rule. Now that you understand this approach, you can apply the same two-pointer idea to many other problems. Next, we will look at problems like valid palindrome, two-sum on a sorted array, and a container with most water. The pattern stays the same, only the condition for moving pointers changes. If this problem made sense, the next ones will feel much easier. Thank you for watching. If this video helped you to understand two pointers better, please consider liking the video. You can also subscribe to the channel for more interview-focused explanation like this. And don't forget to click the bell icon so you don't miss the next video in this series. I will see you in the next one.